I'm Ken Tate. I'm the Director of External Relations for the Department of Computer Science. On behalf of the university and the college and all the faculty and staff of the Department of Computer Science, it is my honor to welcome you to the LabCorp Leadership and Technology Speaker Series. So I hope you're in the right place. It's always my honor to be able to welcome you, and I get asked this question a lot, how do you guys come up with the speakers? And quite frankly, I get a lot of suggestions from students. I get suggestions from, in this case, faculty members, and it takes sometimes years to get them here. That's the case tonight. The speaker and I actually started emailing and talking about this 3 years ago, maybe 4. He's a busy person, very busy man. He was actually scheduled to be the last speaker in the Fidelity Investment Series when it was sponsored by them, the last speaker of the spring of 2000, and then COVID hit. So we're very, very happy to have the speaker. I'm not going to introduce him. I'm going to turn over that responsibility to our department head, Dr. Greg Rothamel, at this time. But again, very glad to have him. So, Greg?
Thank you, Ken. And let me just echo Ken's comment and thank LabCorp for sponsoring this series. Today we're honored to welcome, as Ken has said, Dr. Gary McGraw as our guest speaker. Gary is a co-founder of the Berryville Institute of Machine Learning. He's a globally recognized authority on software security and the author of 8 best-selling books on the topic. His titles include Software Security, Exploiting Software, Building Secure Software, Java Security, Exploiting Online Games, and 6 other books. And he's an editor of the Addison Wesley Software Security series. Dr. McGraw has written over 100 peer-reviewed scientific publications. He serves on the advisory boards of Legit, Irius Risk, Max My Interest, Protopia AI, and Secure Code Warrior. He has also served as a board member of Cigital and Codescope, acquired by Synopsys, as advisor to CodeDX, also acquired by Synopsys, Black Duck, also acquired by Synopsys, Dascient, acquired not by Synopsys, but by Twitter, Fortify Software, acquired by HP, and Invotus, acquired by FireEye. So that's a lot of acquired buys. Gary produced the monthly Silver Bullet Security podcast for IEEE Security and Privacy magazine for 13 years. His dual PhD is in cognitive science and computer science from Indiana University, where he serves on the Dean's Advisory Council for the Luddy School of Informatics, Computing, and Engineering. Please join me in welcoming Gary McGraw.
Thank you. Thanks. I'm going to demask. I'm triple vaxxed for all of you people out there. And we have a barrier. So let's talk about security engineering for machine learning. I thought I would talk about my background a little bit. You heard about all the companies that I used to advise that got acquired. But I'm a retired guy. And when I retired, I thought, gosh, there's an awful lot of hype about AI and machine learning these days. And I wonder how much of that is real. So I started reading machine learning papers again after 25 years. And before that, I published a few things in machine learning as a grad student in the 80s. 1989 was my first machine learning paper. And you know what? We've made some progress in machine learning and AI, but we've made a lot less than you think. Most of the progress is computers are way, way faster, and data sets are way, way bigger, and there's lots and lots of data out there. But many of the things about machine learning that we knew about in the 80s are still applicable today, and many of the algorithms that we're using are the same. So while reading these papers just for fun, it sort of struck me that the people that were working on this technology weren't really thinking much about security. And as a person who thinks about security all the time, I couldn't help but think, gosh, these systems have an awful lot of risks in them. So we started keeping track of that while we were reading papers, and we read some papers about what's called adversarial AI, or attacking machine learning, stuff like that. And we read a lot of papers about just plain old machine learning, and we started to identify risks. And what I'm going to talk about today is the results of that work, where in the great town of Berryville, which has a population of about 3,000 people, we don't really do much machine learning. We do a lot of cow-type stuff. I live on the Shenandoah River in the middle of nowhere, but I'm going to give this talk soon for my community, which is going to be a blast. And I'm going to practice out the introduction on you people, who I'm sure know more about machine learning than the average Berryville cow does. So that's good. And I want to kind of introduce the notion of what we mean when we talk about artificial intelligence these days and how that's changed. But then, most of the talk is going to focus on risks in machine learning. Now, an important thing that I want you to come away with is that we spend a lot of time in computer science talking about, in computer security, talking about vulnerabilities and defects. And most of the time that we spend talking about defects is spent talking about bugs, particular bugs in a program on line 57. And we spend very little time talking about flaws at the design level. Now, my contention after working in software security for 25 years is that we really have got to spend more time thinking about design flaws. So what is a design flaw anyway from a security perspective? Hopefully, when I show you a bunch of design flaws that I think are built into machine learning tonight, you'll get a feeling about that. But sort of the bigger picture, even bigger than machine learning today, that I hope you come away with, is that we really need to focus some attention on thinking about design problems in computer security and in software security. So I'm coming at this from that angle. I thought I would start with an introduction to ML. So here's a gentle introduction. So we all know that computer programs mostly specify very clearly how a thing should be done. So for example, if we want to know what a triangle is, we might specify that we need to look for intersecting line segments that intersect in a certain way, and that will be the definition of a triangle. So we know how to do the thing we're asking the computer to do. When we write a program, we need to specify exactly how, and you know how frustrating that is because machines do exactly what we tell them to do, which is often not what we meant to tell them to do, but they did what we told them anyway. Anybody ever have any trouble with that in here? No, yeah, everyone. The problem is that sometimes we don't know how to perfectly describe what we want to get done. That's one problem. And the other problem is if we are able to describe it once, what the description may end up being is often way too brittle, way too like a computer and not like a person. And that's what machine learning is about. Machine learning says, well, if we can't really describe how in a series of steps in a program, how about if we just describe what? We say, that's triangle, 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 not a triangle, 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 not a triangle. And we just do that a million times. And every time we do that, we adjust the thing statistically so that it learns what a triangle is. So the difference between normal computer programming and machine learning is the difference between describing something exactly how versus describing what we're after. I hope that's clear to everybody. Machine learning will do this, but it often cheats. So we might say triangle, not a triangle, triangle, not a triangle. A famous example that turns out to be a fake example, but it's still a really good one, is a machine learning system that's supposed to classify huskies versus wolves. And the people that talked about training up this model said, we gave it a bunch of pictures of huskies and wolves, and we trained it up until it was really good at that. Then we showed it some new pictures of huskies and wolves. and it was pretty good, but it turned out it wasn't really a husky versus wolf classifier. It turns out that what the machine learning algorithm learned was that every picture of a wolf has snow in it somewhere. And so on the training set, it got the training set exactly right, adjusted the weights, it all seemed like it was working. And then when the thing was out in production, it didn't work the way it was intended, because it turned out that what got built was a snow detector and not a husky versus wolf classifier. Now, this is a well-known problem in machine learning. I thought that was a real example, by the way, and 2 weeks ago we chased it all the way down, like where did that wolf-husky thing come from? And it actually came from a paper about representation, talking about explainable AI and explainable ML. And it was used as an example there. So that's a totally fake example, which is a real bummer, because I really liked that example. And I told a lot of people that it was real, but it's not. However, there are a bunch of things that really happened in machine learning that are just as silly. My friend Doug Blank once programmed a neural network to try to figure out what a word was. It was supposed to determine an English word versus not an English word for 3-letter words. And so it was supposed to learn something like an English word is a consonant followed by a vowel followed by a consonant, like dad or pop. And you know what the thing learned? Although it learned its training set perfectly. An English word is something that's not a K, followed by something that's not a K, followed by something that's not a K. And that was a perfect classification. So when I was a grad student, we called it the not a K problem. But you can call it the wolf-husky problem if you want. It's the do what I mean, not what I say thing, which we were trying to avoid in the first place by not having to write a program and specify exactly everything, but instead have the thing be learned. So that's kind of what we're up against when we're doing machine learning. Now, there's a lot of confusion about what machine learning is versus AI versus all sorts of other gobbledygook. And so I want to steal this piece of history from Melanie Mitchell. These are slides that she made, and she gave me permission to use these. Her book, Artificial Intelligence, A Guide for Thinking Humans, is a very good one, by the way. So check that out. Melanie was a student of Doug Hofstadter, like me. So from the 50s to the 80s, AI was a big old thing, and machine learning was a little thing in the big thing, and deep learning was a really, really little thing. Maybe we had lots of logic-based AI, we had unification problems, we had some statistical inference models, maybe, mostly symbolic. Then perceptrons were invented, and we started doing some kind of machine learning that was a little bit different that way. In the 90s, things got much bigger in machine learning. And deep learning, though, was still a little tiny thing, because it turned out in order to do all the computation required for a bajillion layers in a network, you'd just eat a computer alive. One of the first models I ever wrote was a fully recurrent neural network with 4 nodes. And it would eat the biggest computer we had in the computer science department alive, just trying to compute those 4 nodes and how they all interacted in a dynamic system. So, we've come a long way. Now we have computer cycles all over the place, and we can, just get GPUs and just build gajillions of layers. And some of the networks that we're building are immense, like GDP3. The language model cost $12.5 million to train, but that's because it has billions of connections, billions. And the training set is trillions of things. That's that's more than 4. So we've come a long way. But now, when you look at artificial intelligence, it looks something like this. Everybody just means deep learning. And, there's a lot of other AI out there. There's a lot of stuff we're ignoring about representation and one-shot learning and some other stuff that we seem to have forgotten about temporarily. Maybe we'll come back around to some of that stuff. But suffice it to say, when you read about stuff that artificial intelligence understands how to play Go or whatever, remember what we're really talking about is deep learning. So what is deep learning anyway? What's the whole idea? Well, we already talked about the how versus what. Now I want to tell you what inspired this whole thing, and that is neurophysiology, sort of misunderstood. Or if you stand way back from neurophysiology, way, way back, and squint, this is what it looks like. So we have a dog, or a picture of a dog that goes into the retina, and it does some edge detection in the retina, and then there's some simple shapes, and then we get into V1 through V4, and we build more complex shapes, like building up the representation, and eventually we get faces and objects being recognized. So this is a neural network made up of neurons in your brain, and the activation feeds from your retina into your brain, and you say, dog, right? So that's the inspiration. So a convolutional neural network looks like this. We have similar input, maybe a picture of a dog. We got a bunch of layers, and then we have a classification module, so activation feeds up through the network. And at the end, we say something like 85% dog, 85.6723% dog. Nobody says that, but that's what these models do. And they also say, I'm sort of 2% confident that that's an 87% dog, which is interesting. But what we do when we train these things up is we show it a picture of a dog, and it says, not sure, but not a dog, maybe 90% cat. And you change the weights all the way through the entire network, all the way feeding back, all the way to the input, just a little bit. And you do that millions and millions of times, just adjusting those weights. That's all you do. The technology for adjusting those weights was really kind of hit upon in 1989-ish, when this great idea of having a sigmoid function for the activation function came about by McClellan and Rumelhart. And the idea was, before that, it was a totally linear function, and perceptrons could only compute certain things. There's a famous book from ancient computer science called Perceptrons that takes neural networks down. Says you can't compute certain things because of these theoretical properties. Interesting book. But when you change that thing to a sigmoid, all of a sudden you could do calculus on it, and that changed everything. And then we could talk about gradients, and we could talk about gradient descent, and we could do machine learning in a different way. What's happened in the last few years is just big piles of computers doing it on these things. Now here's a question to ask yourself. Are neurons in your brain really like neurons that we use in a convolutional neural network? And the answer is nope, not much at all. In fact, a lot of the calculation that happens in dendrites and not in the axon, and there's a lot of stuff that we're just sort of eliding. So we've built a model of a neuron that's super simple. And you know what's cool? We can compute a lot of interesting things even with that dumb version of a neuron. So imagine if we had a smarter version that actually was more realistic. We were getting computers that are solid enough to be able to do that now, but not many people are doing that yet. Much of convolutional neural network stuff and deep neural network stuff is not really informed by neurophysiology yet. But that time is coming soon, and we should expect some sorts of big changes then, even more revolutionary than what we've seen now so far. So these things can do a lot of stuff, and different kinds of networks have slightly different architectures, but networks that understand language, like GTP3, exist. You sometimes interact with them on your phone, I'm sure. Networks that can win Go against human experts and even come up with new moves that no one ever imagined would be a real move. I'm sure you're familiar with AlphaGo, exist. But these problems are not really problems of cognition. In fact, when we talk about language understanding, what a convolutional neural network is doing, like GTP3, is not at all like what you're doing when you do language processing. Does it work for some simple tasks? Yes. But does it fail in hilarious ways? Oh, yes. It's kind of fun to play with these things. And you go, wow, that really doesn't understand anything at all. It's just kind of like, anybody ever write an n-gram program? Turns out you can make language that looks kind of sort of okay. But remember, what we're doing is we're training this statistical pile of stuff on just jillions of examples. So one of the things to think about is, where do those examples come from anyway? Should we have trained it to be like Reddit? Really? 8chan? I don't know. Seems like a bad idea. But we're just scraping data from everywhere. We're just like, we're going to scrape it and just see what it learns. And so we can make the thing learn bad stuff too. What we wanted to do at BIML, the Berryville Institute of Machine Learning, was to talk about risks involved in all machine learning models. And so the first thing we had to do is build this generic machine learning model. This is our generic model. It has 9 components. And later, what I'm going to do is tell you about risks associated with either one of those 9 components or the system as a whole. And just to steal a little bit of my own thunder, we identified 78 risks, not 2, that are applied to this generic model. And that's what I want to share with you today. So we use this model to think about the risks in each component, and it should be pretty straightforward what these parts are. You'll be able to see that again in a minute. But first, a little bit of whining. I like to whine because I'm an old, white, retired guy. So I get to whine, say, get off my lawn and stuff like that. And the get off my lawn about security is that nomenclature really matters. Some people are calling this field adversarial machine learning, which is fine if you're only concerned with attacks. But I think that computer security can't be only concerned with attacks. Instead, we have to be concerned with building stuff that doesn't suck. It turns out that you get a lot more security out of building stuff that doesn't suck than you get trying to patch the attack of the day. Really, honestly. And we've spent about, I don't know what, 25, 30 years trying to patch our way out of this problem or unpaint ourselves out of the corner. But it's not working, and we're producing software that sucks as much as it used to suck, which is terrible. Now we're producing it faster because CI/CD, DevOps, woohoo, which means bad software faster and also a bad configuration to run it on. So I don't like calling this field adversarial machine learning. I want to call it security engineering for machine learning or machine learning security. Now, the other problem is if you call it machine learning security and you say, yeah, I'm working on, machine learning security, people almost always think, well, you must be building a security thing using ML. What are you doing? A security feature. Well, I don't really care about that. I care about machine learning doing anything. Is that machine learning itself secure? Not I'm using machine learning to authenticate somebody. Right? So I want that to be clear too. So when I'm talking about machine learning security, I don't care about security features. I'm not talking about crypto. I'm not talking about authentication. I might be talking about data security though, and I'm certainly talking about security engineering. My take on the computer security problem is we must engineer our way out of this. And the way to do that is to think about design and to think about risks while we're building something. So we want to apply all of that thinking from software security to machine learning. So a little aside about attacks, because I know if you came to a machine learning security talk and nobody talked about attacks, you'd be really mad and you'd be like, that guy, he didn't talk about the sex appeal stuff, right? Like, what about the adversarial thingy and the stop sign with the tape? Right, so let's talk about that a little bit. First of all, there's an awful big list of attacks. But we think they can be boiled down to these 6 things. Like if you know these 6 things, you know all the attacks we've found so far. And the 6 things are really simple. One column is manipulation, and the other is extraction. So either we screwed around with it or we pulled it out of there. And then you can pull it out of the data or the input or the model. So model extraction is, we copy some parameters and we just extract the whole model and we build a perfect copy of the model, which we can use. Data extraction might be, oh, it got trained up on a lot of data. I wonder if we can just pull that data out of there. And it turns out that, yeah, often you really can. In fact, GTP3 knows an awful lot of social security numbers, which is not supposed to know that, but it was in the training data somewhere. And it's big, so it memorized pretty much everything. It's in there somewhere. You know, so that's a thing to know. Like, this is a super simple attack taxonomy, and we need to think about that. We need to know about that. But what we really need to know is how to build things that are not susceptible to those attacks. And to me, what that means is identify risks. If we can think about risks while we're building a system, then those attacks won't even be able to happen in the first place. That's the idea. In my world, attacks happen because you screwed up. And the screwing up is a risk, not the attack. Attacks require intentionality on the part of an attacker, on the part of somebody going after you intentionally, trying to screw you up. Now, you have to think about that for sure, and you should know about attacks. But the way to solve it is to think about big families of risks so we can eradicate those risks or at least manage them while we're building a system. My view is that no system that's unreliable and fragile can be secure. And so let's talk about risks. So we started with this ML risk analysis, and we identified 78 risks tied to those 10 components. And we mapped known attacks and attack surfaces to those risks too. So you can check out the work that we published under the Creative Commons right there. You can reuse that. You can put it anywhere you want. It's under the Creative Commons. So check it out. And it's got a lot more material than we're going to cover today. What I want to do instead of telling you about all 78 risks is just tell you one for each one of these components. So think about the fact that we're going to cover 10, right? 9 plus 1 extra. And there are 7 times more, or maybe 8 times more, really. The first thing is data. Remember that part where I said, yeah, we scraped it off of Reddit and we just shoved it into GTP3 and it learned all that stuff? Well, you got to ask yourself, where'd that data come from? Who can screw around with that data? And if I go back there and look for more data like that, is it going to be the same tomorrow as it is now? What are the sensors I'm using? All these things, because data is the machine. Remember, we're taking this kind of tabula rasa thing with a bunch of neurons and random weights, and we're using back propagation to adjust those weights so that it learns the data. That means the machine really just is the data, if you think about it. So you got to be careful about your data. If you give it really dumb data, you're going to come up with a dumb machine that knows the dumb data really well. If you give it racist data, you're going to come up with a machine. You're not supposed to sit there because of breathing. But that's, sorry. But you can sit there. That's fine. Yeah, sorry, man. So you're not supposed to, so when you think about, sorry, reset. When you think about training, you've got to think about your data set. You got to think about bias in your data. You got to think about where it came from. You got to think about who can manipulate it. And we'll get into more of that as we go along. There's lots of raw data out there to be manipulated. A good example of a risk here is training up a machine learning model on data that's confidential. Say we have a way of identifying Russian tanks, for example. You just say, oh, it's in Ukraine, it must be a Russian tank. So terrible. So here's the deal. If you train up a network on confidential data, those confidential data are in the network. They're in there. So if you train up a network on GDPR protected data in Europe, should the network be protected by GDPR? Nobody knows. They're trying to figure that out. We're not sure yet. If you have classified data from the Pentagon and you train the neural network on those classified data, is the neural network supposed to be classified? Oh, probably everything's classified. So know that if you put confidential data inside of a network, that if we train it up on that some of those data are built right in through the training. And attacks to extract those data, sensitive and confidential information, are well known, and there's a whole bunch. And you can even do it through normal use. You just sort of stick some input in, and out comes the stuff that you're not supposed to know. So that's one of 11 risks in raw data. Now, the next thing we need to know is transform that into some sort of format that machines can actually eat. Now, the raw data often has to be manipulated in some way. So I want to talk about the human part of pre-processing and massaging and managing data in machine learning. It turns out that the way data are tagged and bagged or annotated into features or whatever can be directly attacked, introducing all sorts of bias into a system. And an ML system that's trained up on examples that are too specific, for example, won't be able to generalize well. Much of the human engineering time that people spend trying to make a model work is spent kind of screwing around with the data until the thing finally works. And that's the part that a lot of people don't talk about. You can't really just throw any data at a machine learning model. You have to think about what your data sets look like and what your transformations look like. So that's an example of data set assembly risk. Then we move on to the three big data sets that really matter: training, and then validation, and then testing. These are kind of separate ways of making sure that the thing is on track. It is a black art trying to figure out how to do training, like how to build a training set. So you got a big giant set, you want to boil it down to something that gets the whole picture across, but you know, if it's too small, the thing will just memorize what you're doing. You got to figure out kind of the between generalization and memorization, and it turns out to be hard to build a good training set. And there's not much good information about how you do it. Mostly you do it by just doing it and see what happens. And sadly, when you read a lot of papers in machine learning, they say things like, yeah, we set that parameter to 6. And you go, okay, what's 6? Well, we set it to 6 empirically. Oh, empirically, what's that mean? Well, it means we set it to 4 and 3 and 32 and 6,412 and 6 worked. So we set it to 6. Really? Really? And sometimes you're like, well, let's try that ourselves. And you set it to 6 and it doesn't work. And you go, damn, why didn't that work? They said 6. So now people are at least publishing their data sometimes along with the model. But it turns out, if there's a lot of data, that's a big, giant glob. Your disk drive's not even big enough to hold that glob. Plus, you know, if you're going to do something at, say, Facebook AI level, you're going to need just a few cycles. So Lori said she could support that in her budget. So, you know, grouping into these training and validation and test sets is tricky, and it's susceptible to poisoning attacks. In fact, all three of the first components, raw data in the world, data set assembly, and data sets, are all susceptible to this idea of poisoning. And poisoning is when an attacker intentionally manipulates data in any or all of the three of the first things, possibly in a coordinated fashion, to cause the machine learning training to go awry. So we intentionally poison the data. We throw in a cat every once in a while instead of a tank or whatever. And it turns out that data poisoning is much more sophisticated than we thought. And machine learning algorithms, for example, are susceptible to the order of their training set. This is something that Ross Anderson recently found out and published last year. Really interesting work, because it turns out that when you start out with a stochastic space, your initial conditions actually matter quite a bit. And the order of your training corpus matters too. And in fact, one attack keeps your training set that you came up with intact, but changes the order of that. Now, of course, other attacks might just plain old screw around with the data or screw it up. And the question is, how do you find out about poisoning? What do you do about poisoning? Where did the data come from anyway? Now think about the world of fake news these days. Humans can't even figure out if their data feed is poisoned. Really. And now machines are susceptible to that even more than humans. This is not a good thing. So that is an example of one of the 7 risks that we found at the data set level. Next, we move on to the learning algorithm itself. Now, there is a big distinction between systems that are online versus offline in machine learning, and here's what it means. So when you're training up a system in the training phase, you sometimes just freeze it, and then you ship the frozen network out to operations where you feed input into the network, but it doesn't learn anymore. It's done learning. Other times, you train the network, and you put it out there in operations land, but you keep on training it while you're using it. A good example of that is the Google Translate algorithm, which had a hilarious feedback loop, although we've never been able to chase this down, but I know it's really true, where the Google Translator was training itself on stuff it found on the internet, and it found its own stuff on the internet. It started eating its own tail. And boy, did it think it was good. And getting better all the time, in fact. Wow, it's so much better. So you got to be careful when you're getting data from out there that you don't start eating data that you produced over there because you're eating all the data. That's another thing that can happen, these feedback loops. When an algorithm is online, you can see what the risk is. It's pretty obvious. The risk is that when it's out there being trained, that somebody can intentionally manipulate it through normal use and move its operational profile somewhere else where it's not supposed to be. So an attacker intentionally feeds some crap to the network, moves the network to where it's not supposed to be, and the network learns to do the wrong thing. Perfect example of this is a chatbot for Twitter called Tay that Microsoft produced. Anybody heard of Tay in here? And Tay was supposed to live on Twitter and learn to do Twitter. And you know, what do you learn when you do Twitter? Well, you learn to be a racist, misogynistic asshole. So Tay learned that really fast. It really did. They learned to be a perfect troll just immediately. It was so embarrassing that Microsoft was like, we must kill Tay. They just unplugged it and threw it away. Because it was getting a raw feed from Twitter, and the trolls were like, ooh, let's make that learn some stuff. And it did. So that's a kind of obvious example of an online attack. There are 11 risks in this category, so there are 10 more. Then we get to evaluation. So, you know, this is where you try to figure out if your machine learning model learned from the training set what you wanted it to learn. And remember, the tricky bit of machine learning is you want it to learn by example, but you don't want to create a lookup table. Turns out that lookup tables that haven't generalized to anything else aren't that interesting. Like imagine the triangle example where we have the 8 triangles that I showed. Triangle, 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 triangle. And then we show it a whole new triangle just rotated a little. It's like, nope, nope, not triangle. That's not on my list of 8. That's not what you want it to do. But, you know, multiply that by 1,000,000 and you see what the problem is. Because these things can actually memorize. They can do what's called overfitting of the data, where there's no fuzziness anymore. The part that we want in deep neural networks and convolution networks especially is some sort of vagueness around the thing that it learns. So it's sort of a pile of fuzzy statistics. Not a perfect answer, but yeah, that's probably a triangle. That's why 85% dog. Now when you have a very powerful network, that's sometimes hard to get because the thing can just memorize everything. And it will. So that's a tricky thing. Overfitting is something we've known about since the 80s, but it really applies the bigger our machines get. So that's one example of the 7 risks in evaluation mode. Then we get to inputs into the model itself. Now the difference between the raw data in the world and the data set assembly and the training data is that that's how we make the machine learn. And then later we operate the machine, and we operate it on stuff that it didn't learn, but it's the same, you know what I mean? So we got a bunch of pictures of dogs and huskies and wolves, and we show that to the network, and it learns with our data set, but then we want new pictures of dogs it hasn't seen before, and it's supposed to do the right thing. So, you know, the real question that I found out recently is that component 6 turns out to be way more important than I thought. Operationally, what a neural network sees is 95% of that. That input accounts to 95% of what the network sees in its lifetime. The training set is 5%. So there's a lot more risk in this input in operations than we were thinking, which is kind of interesting. I didn't really think about that until a couple of weeks ago. So we've got to focus a lot more attention on this category. When we wrote this paper, we weren't thinking about it so much. But we were thinking about something that everybody knows about called adversarial examples. An adversarial example is really easy to explain. It's just malicious input for machine learning. That's all it is. Nothing complicated. Now, the funny thing is that since neural networks have representations that we don't really grok, sometimes adversarial examples can be something that a human would look at and go, well, that's obviously a school bus. And the neural network says, well, it looks a lot like the thing that you said was a school bus before, but actually, that's a leopard. And you go, wait, there was no change. But there was a change. You just changed one little pixel just a little bit, and it went from school bus to leopard really quickly like. That's a real example. That happens with stop signs. Probably the most famous example comes from University of Washington and University of Michigan, where some people put some tape on stop signs for a sign recognition algorithm, and the thing was totally confused and read a stop sign with tape as a speed limit 45 sign. And we're going to let these things drive themselves. Yay! Yeah. So, you know, if we don't understand how the thing does what it's doing, then it might do something surprising. And I guess, you know, in software we've always said, that's just a feature, it's all good. Because we didn't have a specification, so can't be wrong. Just be surprising. But, you know, that's not so good when we have these machines acting out in the world. So that's an adversarial example, and that's sort of taking up all the oxygen in the room. I'm sure that you've heard about these already, the stop sign example. And what people mostly talk about in machine learning security has to do with this particular attack. I'll show you some more later. It is an important category of attack. In fact, I think it's the most important risk in the pile. But it's not everything. There's 77 other things that can go wrong. So we can't just focus only on that one problem. Okay, moving on. Now we get to the model itself. So, you know, the risks associated with a fielded model are very similar to the evaluation risk because, you know, we're running a machine and seeing if it does what we want it to do. And an example of a risk here is a Trojanized model. So model transfer is a real thing. And model transfer works like this. You train up a model to do something like recognize circles, and you spend a lot of money making a circle recognizer. And then someone from marketing comes along and goes, hey, we got to have a oval recognizer. Circle's not good enough. So instead of starting over again and training up an oval recognizer, we just start with a circle recognizer and adjust it by doing some training on top of the thing we already trained. That makes sense? It's way cheaper because some of these models, like GPT-3, the language processing thing that OpenAI built, costs a lot of money, like $12.5 million. And so you want to start with something you've already got and sort of fine-tune it a little bit. That's called transfer. Now, when you're transferring the stuff you want to transfer, that's great. But if somebody trains up a model and puts it out there in the world for everybody to use, and it has some built-in functionality that's not supposed to be in there, but they didn't tell you and nobody's really sure, that's Trojan functionality. That's like a Trojan horse, exactly what we know about in computer security for, I don't know, 1 million trillion years, and even the Trojans back in the, well, never mind. So it's been around for a while. And that idea they're calling backdooring in machine learning, in adversarial machine learning, which is really dumb because we already have a word for that called Trojans. And so that's one of the risks at the model level. Now we move on to our inference algorithm itself. And of course, you know, there's more risks sort of associated with a fielded model. And now we're getting to the output itself. And we built the whole thing in order to create this output anyway. We wanted to say dog or tank or don't give that person a loan or whatever, right? So the problem, one really very important, we already talked about the online thing, making the thing drift, so I'm not going to talk about that one. I'll give you another example. A problem of inscrutability. Like, we trained it up, it worked on our training stuff, it worked pretty well on our evaluation stuff. We've had it fielded for a long time and it sort of just works, you know? We're giving some loans, we're not giving some loans, everything is cool. Well, how does it work? I don't know, it just sort of works. That's not good. That's when people don't know the difference between, say, a neural network and magic. Oh, it's just magic. It does the magic thing. We always count on the magic thing. Every time we put in something, it gives you the right answer. Well, how do you know it's right? Well, because it did it. What? That sounds pretty dumb. So the problem with these gigantic models is often we really don't know how they do what they do. They just do it. We know the input-output stuff. We can test it. We can put some stuff in and see what it does. But we don't know how it does it. Oh, remember that first part of the talk about the how versus the what? We don't get the how automatically when we give it a bunch of whats. Triangle, 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 triangle. Who knows what the thing is thinking? It's certainly not thinking like people think. Maybe it just found a pointy up angle. Like that's what it turns out to be, like the snow finder in our husky dog example. So inscrutability is really problematic, especially when we start with biased data. And we start with biased data a lot. Like, let's think about this country 50 years ago and banks and how banks decided to give people loans or not. Now let's decide whether we should take those old data from our biased racist society and train up networks to do that now. That seems pretty stupid, doesn't it? But that's what we're doing. That's stupid. We have got to stop that. And it has to do with, you know, the inscrutability. Well, we aren't biased. We just had the machine do it. Whoa, 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 whoa. Watch out for that. That's what's coming, right? We do need to know how the thing works, and the inscrutability thing is a gigantic problem that we can't ignore. All right, and we get to outputs. This is where we actually just say cat or dog or whatever. Obvious attack is we just get between the machine learning component and the rest of the system, and we change it. And you know what? Since nobody's sure how the network does what it does, well, they're not going to notice if we changed it. We interpose, but since it's a magic box, the magic box did a magic thing. Who knows? Oh, everything's fine, right? So, you know, as our culture gets dumber, we have to be super careful not to fall in that hole. So that's an example of 9 risks, and I want to give you one system-wide risk. This is going beyond all of those 9 components in our model and thinking about what happens across components or between components. And one example I've already alluded to is black box discrimination. So a lot of data-related risks lead to behavior in an ML system that, say, gets trained up on personal data or, you know, feeds into high-impact decisions like whether or not to do surgery, credit scoring, employment, medical diagnosis, recidivism. All of these things pose a great deal of risk because if we have biased data that we put into the front of the model, then what we're going to get out might be misaligned. It might just be taking into account things like gender or race or sexual preference or age, and operating the system may result in this discriminatory behavior. We already see systems that are doing that. We know the systems are doing that. And we've got to, those of us in tech have to say, whoa, 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 wrong data. Try that again. Which means we need to know how the things work, and we need to know that they'll fall off the track. It's not that all machine learning is evil and bad. It's just a hammer. And guess what? You can use a hammer to smash stuff. You can use machine learning to do bad things and good things. Don't forget about the bad things, just because the good things are coming along. We know that from all of technology, but it really matters in machine learning. And it matters enough that the big companies are really worried about it, enough to fire people over it. So think about that one. So I've given you a lot of risks, and I want to just sort of give you a quick hit of the top 5, and then we'll be done. So what are the top 5 out of those 78 risks, or the 10 that I just showed you? Number 1, adversarial examples. This is kind of the most commonly discussed one. Here is a real example. So school bus, pheasant, Mayan temple. Mask looks like a school bus and a pheasant and a Mayan temple. I mean, leopard, leopard, leopard. Right? So that's really weird. And it turns out that the representational space that's inside of these things is kind of tricky. And you can find these edge conditions automatically if you know a fair amount about the math. So you can compute adversarial examples, and then you can compute defenses against adversarial examples, and then it's just like turtles all the way down. So there's like an arms race going on between the people who are making adversarial examples and the people who are making anti-adversarial example stuff. And it's kind of silly, but that's happening in the literature. So, you know, you can fool an ML system by providing malicious input to it, small perturbations sometimes that people don't know, get the categorization wrong, and this gets a lot of, you know, coverage because it's pretty cool that you can put tape on a stop sign and it says speed limit 45 to the machine. That's like the press is all over that stuff. So this is important category of risk, but not the only one. Number 2, which I think I would make number 1, given my druthers these days, is data poisoning. Where did the data come from? Who can screw around with the data? Is that the right data? You know, what did we make that thing learn anyway? Do we want it to learn that? And we have to watch out for the not a K problem. But intentionally manipulating data used by a machine learning system is pretty easy to do. And you know, the question you have to ask yourself is, what fraction of the training data can an attacker control? And if they can control it, what could they do to us? So here's a question. Does the Department of Data Science even think about that? Probably not. They're just like, oh my God, there's so much data. What are we going to do with all this? Not, we should throw some of this out. But maybe we should throw some of it out. Number 3, online system manipulation. We move the network to where it shouldn't be and we get TAE. Right? So this is a complicated risk because this is not just the data science people or the machine learning people. Now we got to involve the operations people. They got to keep an eye on the thing. Hey, did that thing become, oh no, turn it off. Right? So somebody has to watch when the thing is out there. Well, a lot of us builder people, we're not used to watching the things we build. We like to just like do agile. We agilely run away from the new scrum over there. Run away. Right? So, you know, that doesn't work so well with online system manipulation. Number 4, transfer learning. This has to do with the Trojan functionality that I was talking about before. But remember, you know, for economic reasons, we're taking stuff we knew before and we're kind of refining that and turning it into a new thing. And if the old thing has stuff we didn't want or behaviors that we can tickle or failure conditions that we can find out, well, we can really screw around. And it turns out that transfer learning, you know, these transfer stuff is very, very common because it's so expensive to build these models. It also turns out that the PyGlobs, PyTorch stuff, are just sitting around in the clear on servers and people just get them. It's like, where did you get that? Ooh. This is like, I remember in the 80s when we used to just download programs and run them on purpose. We didn't think, where'd that come from? Who would do a bad thing to my computer? And now it's just like, why would you run that? So that applies to machine learning as well. And number 5, getting right back around to where we started from. It turns out that if you train these models on confidential data, the data is in the model, and you can often extract it. So those are the top 5 risks in machine learning, in my opinion. I might change the ordering a bit, but they're all things we got to work on. So the next question, since I've run out of time, I'm not going to answer. But the question is, what are we supposed to do about this? And that's why you're here. So you're supposed to solve this. So sorry. Right, so the answer is part of working on machine learning security is identifying these risks in the first place. So that's good. That gets us a fair amount better than blithely just going on as if these risks don't exist. We know that they're there. So that's a good start. But we're not really sure what to do about some of them yet. Like, how do you tell if your data are poisoned? Oh, not so sure. You know, how can you tell if somebody has reversed your machine learning algorithm that you spent $10 million on and published a copy over there? Good luck with that. Like, there's a lot of things we all need to work on now. Machine learning security today reminds me of software security 20 years ago. And now that's probably a $8 to $10 billion sub-industry. You know, not that big, but big enough. And I remember when we got in on the ground floor of that one. So guess what? Time to get in the ground floor of machine learning security, honestly. There's lots of room here. Nobody knows anything about this. I know the people at Google and Microsoft and OpenAI and Facebook, and we're all just figuring this out. We're all figuring it out right now. So there's a little bit of a literature. There's a lot of stuff out there. There are hundreds of papers, and probably 7 or 8 of them are worth reading. And we have a reading list that we publish every week on our website. Part of the BIML website at berryvilleiml.com is an annotated bibliography. Somebody asked me today in a meeting, I can't remember, it was probably here. Was you? Yeah. Said, well, I'm interested in this stuff, but there's so much stuff being published, and some of it's good and some of it's bad. How can you tell? And I said, well, we write snarky comments about each paper that we read, and we put them on the bibliography. And we also put a top 5. So if you're interested in what I think the top 5 are, go find out. But better yet, make your own top 5. When we started working on machine learning security, the first thing I did is ping all of my friends who are really in machine learning and have been for 15, 20 years and said, what are the best papers? And you know what? Everybody's 5, they were different. So we started with a bunch. But you should have your own 5. So you're doing that, right? When I come back next time? Okay. Where to learn more. So there's some pointers. And now I'm done. So let's have questions for the next 32 seconds. Yes?
So how potent is this as time goes on?
What do you mean?
So as time goes on, if the system is not addressed, how will it affect the market?
It's a big problem already, and it's growing fast because machine learning is beginning to seep into everything. It's kind of like what happened in the 80s when software was seeping into everything. And we were like, wait, that software, it's broken. Yeah. And they were all like, we're still going to run it anyway. Oh, damn, everything's broken. You know, it's that.
So it's be fixed as time goes on when the mistakes are made?
I hope so. I don't think we can patch our way out of this. I think what we need to do is realize that this technology has some issues, and we got to keep those issues firmly in mind as we start to use it. Now, good luck telling that to a VC, right? Because every pitch is like, we use machine learning to do sentiment analysis. You're like, what? Yeah, we can tell by a person's face if they're a criminal. Like, what the hell? What? Yeah, it's like phrenology is back from the 1700s. So we have to watch out for that. You don't get to ask another one. That guy, you wait, later. Yep.
So you foresee like big companies, Facebook and whatnot, working or like taking control mainly of the machine learning security, or will be like a lot of companies that pop up like cybersecurity companies that focus on machine learning security?
Yeah, good question. I think that I know that all those companies are working on machine learning security because I know the people that are doing it. But I'm also doing it on purpose because I don't trust those guys. Never did. You know, I made my first name in security for myself breaking Java when there was this company called Sun and Netscape, which you guys never heard of. And they put out this language called Java, which you have heard about, and we just broke it. And we broke it because we were like, oh, we don't believe that. There's no way they could do that. That's wrong. And we broke it a million times. So I think that it sort of behooves all technologists to go, I don't know if I really, let's look into that. And we need some independent people. Now, cybersecurity is not a field I would emulate. That's a disaster. A lot of snake oil, an absolute ton of bullshit. And if I hear the word cyber anymore, I'm going to have to just choke somebody out. You know, like, I hate that. Because we've lost track of what real cybersecurity should be about, and that is real engineering. Like, you actually have to set out to build something to be secure. You can't just go later and securify it or sprinkle magic crypto fairy dust on it or any number of other things, right? So cyber is a real problem, and I'm not sure what to do about that. And I hope that that's not what happens in machine learning, but it seems to be going that way. Okay. Yes?
Does there risk management framework for AI systems, like how to manage risk if it happens?
No. The closest we've got now is kind of a big-ass pile of attacks that MITRE wrote down that they tried to categorize, and it's just a piece of garbage. It's junk, just garbage list. So no thinking has been done yet on that. We should have one. Why don't you build it? Are you working on your PhD? Oh, well, geez, you got to build something. Yeah. Don't rest on your laurels. Okay, one more, are we done?
One more.
One more!
One more.
Yes!
It might be a nitty question. I just went on your website and I saw the page where you had all the different risks.
Yes.
And then if you click on it, it tells you the different risks associated with each category.
Yes.
So I selected normalizing the data.
Uh-huh.
And there was a risk of having bias for normalizing the data.
Uh-huh.
But generally, you normalize almost every continuous data. So I just want to
Point that out.
perspective on why did you determine it would be more biased and normalizing, and what do you propose to do about it?
Yeah, let me explain one common way that people try to normalize data or build more data, de-bias data. Is that okay?
Sure.
So often people say, well, I have an awful lot of data, but I don't have enough data for this category, so I'm going to make some. A good example of this comes from a Bongard problem. Have you heard of Bongard problems? Where it's kind of pattern recognition. And there's a set of problems known as Bongard problems where you say, you know, it needs to be like, which thing is like that? And people are pretty good at figuring out what the pattern is and continuing the sequence. But there aren't enough Bongard problems in the world. There are only like a few thousand. And a neural network needed more like 1 million to learn the thing. So somebody wrote a program to artificially generate more. But the machine learning statistics were so powerful that they were very easily discriminated those that were built by a program from those that were actual Bongard problems. And that's what happens when you create data. You try to fill holes and you build programmatic data. Often the mathematical group that the thing is in sticks out like a sore thumb to the statistics in a way that it doesn't otherwise. I don't know if that answers the question that you're asking, but we'll have to talk about it further. Did it or not?
I'm not sure I'm not sure we have the same definition of normalized.
Let's talk about it offline. Yep. Yep. Sorry I didn't answer your question or yours, but I have to be done.
You have a statement?
Statement.
All right, so what I got from this talk is for unbiased data, you need to focus on the process rather than the goal, correct?
I think that you have to think about the fact that the data might be biased while you're working on it. Yes.
Yeah, exactly. So
Yep.
focus on the process rather than the outcome of whatever this machine learning does, right?
I think so. I mean, the problem is that often in the outcome, people say, well, it does what I thought it was going to do without really knowing whether it is doing what they thought. Because they, remember, couldn't specify, you missed that part, couldn't specify the how. They couldn't write a program to do it. So they wrote a program to learn by example how to do it. And yeah, it turns out that it's a very powerful technique. It's surprising to me what convolutional networks can do today. But it's not doing it like humans are doing it. And there are some issues that we haven't really thought our way through that we need to think our way through.
Because humans are basically like more vague than logic-based stuff.
Absolutely. Humans have what Hofstadter calls, and what I worked on for my PhD thesis in 1995, fluid concepts. And we don't even know how to model a concept. Probably the closest work to this is being done at NYU right now. And we have a long way to go to get to systems that understand anything. It turns out that playing Go, that's really damn easy. It's a formal system with simple rules. It's easy for a computer. And that's not the way we think. So, you know, we got a ways to go. And we'll probably co-evolve, so we're going to move towards more machine-y thinking, and machines are going to move towards, hopefully, more fluid thinking. Thanks for coming.
All right. Thank you. Thank you, Gary. Before you leave,
I have some little stickers over there. The first people that get to the pile get them.
I just want to say, worth 4 years waiting. This gentleman down here, are you the person that's signing? So if you are a grad student with us and you need credit, see the gentleman in the red shirt if you'll wave your hand. If you need something signed, I'm down here, okay? Thank you.
Thanks, sir. Yeah. Hey, that's awesome. Thanks.
So I've always been a little skeptical of Teslas and any of these self-driving
Oh, man.
cars, and now I'm more skeptical. I'll meet you.
Good. Thank you.
Great presenter, but I don't know anything about computers, but I love your attitude.
Thank you. I appreciate that. Yeah, I think it's important that we try to...